Hello everyone, Kotongwane, the Nated God here. Right, today we are going to look at an exercise based on resulting velocity. Alright, now as you should know by now, with the resulting velocity, it is of utmost importance that you are able to interpret the given information, or that you are able to interpret your problem statement. Right, now in this video in particular, I want to teach you how to interpret some of the keywords, if of course you've been given those keywords in the problem statements. Right, I'm going to teach you if set words or set terms have been given, how you should interpret them. Right, now let's read the problem statement. An aeroplane flies to its destination 300 kilometers directly east of its starting point. The pilot wants to complete the flight in 50 minutes. A wind blows in a northeastern direction at 10 meters per second. All right. Now, one of the terms here that I am referring to is destination. Right. Problems based on resulting velocity have different scenarios. Right, and it is based on the scenario that is based on your problem statement that will determine how you interpret your information. Right, by that I mean, for instance, for this scenario, we've been given the destination, or there's information that suggests the destination that the pilot, right, needs to land on. Right, now, if you've been given any information pertaining to the destination of the flight, right, that information you take as being part of VR. Remember, with resulting velocity, we look out for three velocities: VO, VW, and VR. It is important in interpreting your information, right, or in interpreting the data, that you are able to establish what is it you've been given regarding VO, what is it you've been given regarding VW, and what is it that you've been given regarding VR, if any. Right, but it is important that you understand that in interpreting the problem statement, right, you are looking for any data that relates to VO, VW, and VR. Right, so that is to say destination. So if you've been given anything pertaining to the flight's destination, right, anything pertaining to the flight's destination will be for VR. Right, now for instance here, they said an aeroplane flies to its destination 300 kilometers directly east. Right, so as far as destination, the destination is at a displacement of 300 kilometers, right, and is directly east. Right, so remember I said anything pertaining to destination relates to VR. So that means this here, the 300 kilometers is the displacement, and then also the direction of our destination, which is directly east, is what is the direction of VR. Right, again, everything pertaining to destination relates to VR. Right, so even if they don't specify the term destination, if you've been given that displacement, right, and the direction thereof, then you take those as being relating to destination, hence relating to VR. Right, so that is to say here, from that part of the problem statement, we have something that relates to VR. Right, as far as VR, they haven't given us the magnitude, but they've given us the direction. So VR is directly east, right, as said here in the problem statement. So we know that VR is directly east, right, and then we're also given the displacement. The displacement is 300 kilometers. right? Directly east of its starting point, right? The pilot wants to complete the flight in 50 minutes, right? The pilot wants to complete the flight in 50 minutes, right? So T is equal to 50 minutes, right? A wind blows in a northeastern direction at 10 meters per second, right? Now remember how we interpret wind direction, right? How we interpret wind direction is based on from what perspective the wind direction is given, right? So this one in particular, the perspective is from, or the perspective is such that it is where the wind is headed in, right? So they say the wind blows in a northeastern direction, right? So this perspective is such that it gives us the direction of where the wind is headed in, right? Remember, if the perspective is in, then you use the direction you've been given exactly as it is. So the given direction is northeastern, right? And then if it is northeastern, remember northeast is at the center of the quadrant, right? Meaningly, northeast or northeastern is the same as north 45 degrees east, right? At 10 meters per second. So you've been given both the direction and the magnitude, right, of VW. So as far as VW, right, as far as VW, the magnitude is 10 meters per second. Direction, seeing that we've been given this perspective in, then we use this exactly as it is, northeast. Northeast is the same as north 45 degrees east. All right, so we have all the information we need regarding VW, right? That is all the information we've been given, right? Now, as far as calculations, they said calculate the following: 1.3.1, calculate the velocity of the aeroplane, right? Now, before getting to the questions, let us draw the schematic illustration, right, of the story being told by our problem statement, right? So let's have a Cartesian plane, right? So we'll be using the vector diagram, right? With resulting velocity, I prefer using the vector diagram. It's much simpler, right? Simpler means quicker, right? Now remember, in using the vector diagram method, right, you have three vectors, two of which are the components, and then one is the resultant. So VO and VW are the components, right? And then VR is the vector sum, right, of the two velocities, right? And then remember that I said in one of the previous videos that what is important regarding the vector diagram is knowing how to draw the vector diagram, right? It is not so important which vector you draw first, as long as you have an understanding of how the vector diagram should look like as far as direction, right? So remember, in drawing the vector diagram, we use we use the triangle law, right? And as far as the triangle law, the two components, so VO and VW, must be such that, in terms of direction, must be such that they follow a head to tail direction, and then VR opposes the head to tail direction, right? That is the most important part to understand regarding the vector diagram, right? That VO and VW must be such that they are following a head to tail direction, and then VR must be such that it opposes head to tail direction, right? So it doesn't matter which vector you draw first, right? Even though drawing VO first, if you have enough information regarding VO, right, it is best that you start drawing VO, just because drawing VO first gives perspective as far as what the problem statement is, or the story being told by the problem statement, right? Otherwise, it doesn't really matter which vector you start drawing, right? So for instance here, I'm going to start drawing VW first, right? So VW, right? So VW is northeast. Northeast is in the first quadrant, right? So northeast is going to be somewhere, say somewhere here, right? So that's going in that direction, right? So that's 10 meters per second. Right, so this here is 10 meters per second. All right. And then instead of drawing VO next, right, you can simply draw VR, because we know the direction of VR. Direction of VR is directly east. So VR, we've been told, is in this direction, right? So we know VR is headed in this direction, right? So this here is VR, right? Now, even if you do not say draw the schematic illustration looking at what the story is telling us, right? Even if you cannot really interpret from the given information the direction of VO, right? When you start drawing your vector diagram, right, the direction of VO will come out on its own. Just like in this case, we've been given the direction of VW, we've been given the direction of VR. To complete the vector diagram, we know that we need to draw this one, right, which then completes the triangle. But to complete the vector diagram, we now have to show direction. And as far as direction, remember the vector diagram follows, or in drawing the vector diagram, we follow the triangle law. And as far as the triangle law, the two components of the resultant must follow a head to tail direction. So because this one is going in this direction, then we know that this one will head in that direction, so that, right, so that this follows a head to tail direction, right? In order for this to follow a head to tail direction, right, it means VR must head in that direction, right? I mean VO must head in this direction. So this here is VO, and that completes your vector diagram, right? This is why the vector diagram is important. See, now when having to calculate the magnitude of VO, right, well, the direction thereof, we now have an idea, right, as to what direction is VO. If VO is in this direction, it means it is in this quadrant. If it is in this quadrant, right, depending on which angle you are going to calculate, so the angle, either the angle reference from the x-axis or the angle reference from the y-axis, either way though, whatever direction you get, it must be southeast or east of south, right? This we're being told by the vector diagram, right? Remember, when using the triangle law, well, some of you could be using the triangle law, some of you could be using the parallelogram. And if you draw the parallelogram, this is what you would have, right? Something like this, right? Either way though, if you draw the vector diagram, right, using the triangle law, right, this is what you should have, more or less, right? Either way, you will get the same story as someone who chose to draw a parallelogram, right? Now, question is, calculate the following. Calculate the velocity of the aeroplane. The velocity of the aeroplane, yes. right? Now in calculating the velocity of the aeroplane, let's look at which vectors we have. We have VW, the magnitude of VW. We don't necessarily have the magnitude of VR, but we can get the magnitude of VR. We have the displacement and we have time, so we can get VR, right? We can get VR. Alright, so first calculating VR, this is 1.3.1. So calculating VR, remember that VR is equal to S over T. So that's S over T, right? And this here is equal to, so the displacement is 300 kilometers. Now take note here that the given velocity, right, which is VW, right, is in meters per second. So it only makes sense that VR, or we make VR to be in meters per second as well. So that is to say that we have to convert the kilometers to meters, right? Converting kilometers to meters, I have to multiply by 1,000, right, divided by, and then the time has to be in seconds, so that whatever we get here will be in meters per second. So the given time is in minutes. Now we have to convert the minutes to seconds, right? So converting from minutes to seconds, you multiply by 60, right? If you punch that in your calculators, we are going to get 100 meters per second, right? So now we have VR, right? So we have VW and we have VR, so it means we can get VO, which is the velocity of the aeroplane, right? But before we do that, right, let us complete the vector diagram by showing at least one angle, right? So remember, in using the vector diagram, we make use of either the cosine rule or the sine rule, right? Either way, you are going to need at least one angle, right? And the angle we have here, right, is this one. Remember, they said VO is northeast, right? We have this angle, right? Northeast, right, is this angle, which is 45 degrees. If that's 45 degrees, it means this is 45 degrees as well. So we have that angle, which is 45 degrees, right? And remember now, VR, we've calculated and got 100 meters per second, right? So it means we have this vector and we have this vector, making this angle an included angle, right? So if you have an included angle, it means we can use the cosine rule, right? We can use the cosine rule. Let's call this A, call it B, call this C. So that's B, that's A, and this is side C, right? And then using the cosine rule, we are now going to calculate the velocity of VO, or the magnitude of VO, right? VO is side A, so it means here we will have A squared is equal to B squared plus C squared minus 2 BC times cos A. All right, now you substitute. A squared is equal to, side B is 100 squared plus side C is 10, so that's 10 squared minus 2 into 100 into 10 times cos A. Angle A is 45 degrees. right? Now if you punch all this in your calculator, right, a squared will be equal to 8685,786,438, right? And then to get a, we now use the square root. So the square root of this here right, so the square root of this, punching that in your calculators, you should get 93,198 meters per second. Right, remember all your velocities are in meters per second in this case. Right, therefore meaning, remember that this represents A represents VO, which means therefore VO is equal to 93,198 meters per second. Right, that's the magnitude of VO. Right, the velocity of the aeroplane. Right, that is the velocity of the aeroplane relative to the air. Right, so when they've asked you to calculate the velocity of the aeroplane, right, just know they want you to calculate VO. Right, now normally you would then have to calculate the direction of VO, but in this case, because the second question, right, 1.3.2 want us to calculate the direction of flight, right, you can leave that for 1.3.2. right, so now we do 1.3.2 where we are going to calculate the direction of flight, which we already have an idea. Right, remember that we said if VO is in this direction, right, the way you can tell the direction of VO is by looking at it from the perspective of the Cartesian plane. Right, if VO is in this direction, you then think if this direction would fit in the first, second, third, or fourth quadrant. Right, and obviously this direction can only fit in the fourth quadrant. Right, meaning that VO is such that it is going either southeast or east-south, depending on which angle you calculate, based on if the angle you calculate is a reference from the y-axis or the x-axis. Right, so now we are going to calculate the direction of VO. Right, now if you look here, if you draw VO in the correct quadrant, right, and say we are going to calculate this angle, right, this angle is equal to this one here. Right, so this angle is equal to this one. Right, so it only makes sense that in calculating the direction of VO that we calculate angle C. Right, angle C, right, looking at it from the perspective of the Cartesian plane or the set of axes, right, angle C is equal to this one, and this angle is a reference from the x-axis. So essentially, the angle C will give us the angle of VO reference from the x-axis, right? And if it's reference from the x-axis, the x-axis are east, right? The x-axis are east, right? Whatever angle we are going to get, south, right? So this is the direction we are going to use. Why? Because the angle we are going to calculate, angle C, right, which is equal to this one, is a reference from the x-axis. Right? So we are going to calculate angle C. this is 1.3.2. Right, so we are going to use the sine rule. Using the sine rule, sine C divided by side C is equal to, we have angle A, so sine A divided by side A. Right, so here we're looking for side C, so this will be sine C. We now get rid of side C, so this will be C times sine A divided by side A. And then to get angle C, we have to calculate the arc sine of C, or side C, times sine angle A divided by side A. Right, this is what we are looking for. So this is going to be equal to arc sine of, so now we substitute. Right, now we substitute. In substituting, right, C, side C is the 10. Right, so that's 10. Sine angle A is that 45 degrees divided by side A, which we've just calculated. That's the 93,198. Right, and then if you punch this in your calculators, right, angle C will be equal to 4,351 degrees. Right, so remember, we've already established that side C is equivalent to that angle theta. Right, it gives us the direction, or the angle of direction, from the perspective of the x-axis. Right, this angle is referenced from the x-axis. Therefore, we can say now VO is 93,198 meters per second. Direction of flight, the angle is referenced from x-axis, so east. The angle itself is 4,351 degrees south. Right, so the angle of flight is east, 4,351 degrees south. Right, and that you can even tell from what the schematic illustration is telling us. Right, remember, you are told here that the pilot needs to end up directly east. The destination of the flight is directly east. So the question then becomes, how must the pilot fly in order to end up directly east, taking into consideration the wind vector, right? And that is how you interpret the story, that the pilot must fly in this direction, right? The wind vector will then essentially push the plane, right? It will push the plane, right? The wind vector will push the plane back to course, right? So because of the wind direction, right, the pilot must fly in this direction, right? Upon which the wind will then push the plane back to directly east after 50 minutes or after having flown 30 kilometers in displacement. Right, that is how you would, or that is how we interpret the story being told by the problem statement. Right, either way though, if you couldn't interpret it like that, right, drawing the schematic illustration, right, will suffice without you having really taking into consideration what the story really is, or what the problem statement is telling us as far as how the pilot must fly in order to end up directly east. Right, that is this is how you look at such problems. Right, I trust that this was helpful. Right, press the like button if you like this video, and then stay tuned for more videos on this topic and other topics as well on engineering science and 4. Cheers.